In the vast cosmic tapestry, where stars and galaxies shine brightly, a hidden era known as the cosmic dawn once shrouded the universe. It was a time when a veil of hydrogen atoms concealed the light from nascent stars and galaxies, veiling the universe in obscurity. It was a fierce ultraviolet radiation of the earliest stars and galaxies that, over eons, managed to pierce through this hydrogen fog, heralding the transformation into the luminous universe we witness now. In the quest to fathom these primordial realms, astronomers have long yearned for tools that could decipher the universe's enigmatic beginnings. And the James Webb Space Telescope, or JWST, a marvel of modern technology, has become a key instrument in this quest. This cutting-edge telescope's advanced capabilities have enabled astronomers to scrutinize the very stars and galaxies that took shape in the aftermath of the monumental Big Bang. For months, James Webb has stunned the whole world by capturing early galaxies defying the cosmic rulebook of the early universe. And now, in the latest discovery, James Webb continues to unveil the existence of a bunch of ancient galaxies, unlocking secrets of how infant galaxies started an explosion of star formation in the very early universe. Join us today as we dig deep into how James Webb's new discoveries just shed light on the early universe. Constructed by NASA, as well as Europe's and Canada's space agencies, the JWST is the most powerful off-world observatory yet built. But for a time, the observatory was more of a cruel joke among astronomers. The technical demands of its development pushed the project so far over budget and behind schedule that many suspected it would never launch at all. Despite the debates over the telescope's naming and history, one thing has become abundantly clear this year: the scientific ability of James Webb is simply remarkable. The premier observatory now is already delivering on its promise to revolutionize our understanding of the cosmos during a mission that could simply stretch into the 2040s. The first photos from James Webb went out to the world on July the 12th, 2022, and they were stunners. The clarity and level of detail are unprecedented. Seeing the telescope's new views of some familiar objects, from the oft-photographed Carina Nebula to the planet Neptune, feels like putting on new glasses with a stronger prescription. Each image has created a stir, suggesting that in the coming years the telescope's pictures will infiltrate the public's subconscious just as thoroughly as Hubble's. While every scientist has their favorite astronomical body to image, one of the most anticipated avenues of research James Webb has opened up is the ability to explore what only infrared light can reveal. The history of the universe begins with the Big Bang, which was followed by a period of time during which the universe was hot and glowing. This initial hot period was when hydrogen and helium, the primordial elements that make up the early universe, were formed. As the universe expanded and cooled, its initial glow faded away. About 380,000 years after the Big Bang, the universe went totally dark. So dark, indeed, that astronomers call this period the Cosmic Dark Ages. It was during this time that hydrogen and helium condensed. After 100 million to 200 million years, clouds of hydrogen and helium became so dense and hot that they began to undergo nuclear fusion, and the first stars were born. These stars were monsters. They were hundreds of times bigger than the sun, and they shone white-hot, but they lived short lives. You would think seeing them would be easy. They are bright and unmistakable beacons from the beginnings of time. However, the universe plays tricks on us. The universe has been expanding since it began with the Big Bang. As it expands, it also stretches out the light that travels through it. The universe's first bright blue-white stars emitted light in very short wavelengths. However, the expansion of the universe stretched that short wavelength blue light to a longer wavelength green, then longer still to yellow, and finally to orange and red. Stretched further still, the light of the primordial stars reached infrared. This part of the spectrum is invisible to the human eye, and even to the venerable Hubble Space Telescope, but it is exactly what the James Webb Space Telescope was designed to capture and render. With its overwhelming power, the JWST, the $10 billion machine, has a spectacular mission: to tell the story of our origins in the universe's distant past and relate it to other potential stories, perhaps of other creatures across the galaxy. Let's pause for a second to unpack that previous sentence. To tell our story, that is, the story of life on Earth, we must look back in time, connecting us to the story of the universe itself. Why is that? Well, because, as Carl Sagan famously noted, we are stardust, aggregates of atoms forged in dying stars billions of years ago, before the solar system originated. And those stars, the sources of our ancestral stuff, were themselves forged by other dying stars in a cosmic bootstrap dance of creation and destruction that links all existing stars to the very first ones, the ones James Webb will look at, that emerged only about 100 million years after the Big Bang. That means that stars, like people and all kinds of life, have ancestry too. And just as we can build our family tree by looking at our ancestors, astronomers can reconstruct the evolution of stars in the universe by looking at the very first stars and how they evolved and exploded, their demise giving rise to new stars that lived and died to generate a new crop of stars, and so on. So to look back at the first stars is to do a kind of cosmic archaeology, unveiling the seeds that eventually made stars like the Sun and others possible. That is, stars that can have a cord of planets orbiting around them, with some of them in what we call a star's habitable zone, the region not too far and not too close from the star in order for water to be liquid. This connectivity between past and present is essential to understand life in the universe. And as James Webb looks back, it will also be looking at those planets that orbit stars in their habitable zones to do something extraordinary: map out the chemical composition of their atmospheres to seek molecules that are what we call biosignatures, those that are usually linked to the presence of life. In other words, this remarkable telescope will look both at the distant origins of life, the stars that cooked up other stars that cooked up other stars that cooked up elements of life, and at signs of life itself in other worlds, connecting life's origins with the possibility that we are not alone in the universe. In the quest to understand the first stars and galaxies that lit up the cosmos, James Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. But Webb's findings were exciting in an uncomfortable sense. It discovered the existence of fully formed galaxies far earlier than should have been possible according to the so-called Standard Model of cosmology. According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then the force of gravity pulled together the stars into galaxies. However, the Webb data revealed that some very large galaxies formed really fast, in too short a time, at least according to the Standard Model. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Explaining this excess may require substantial revisions to prevailing cosmological models, changes that could involve the first galaxies forming sooner, their stars shining brighter, or perhaps the nature of dark matter or dark energy being even more complex and mysterious than previously thought. While scientists scratch their heads and wonder if we need to rewrite cosmology altogether, James Webb continues to provide breathtaking new discoveries that could simply upend our understanding of the universe. According to new observations from James Webb, baby galaxies in the early universe ignited gas to trigger explosions of intense star formation. Many early galaxies, like the ones the James Webb Space Telescope detected, were rich with glowing gas so bright that the gas itself could outshine stars emerging from within. These new findings reveal just how common such shimmering infant gassy galaxies were when the 13.8 billion-year-old universe was around only 2 billion years old. The team behind this research found that almost 90% of the galaxies had so-called extreme emission features, meaning they exhibited all that glowing gas. As research lead author and ARC Center for Excellence for All-Sky Astrophysics in 3 dimensions, scientist Ansu Gupta said in a statement, "The stars in these young galaxies were remarkable, producing just the right amount of radiation to excite the surrounding gas. This gas, in turn, shone even brighter than the stars themselves. Until now, it was challenging to understand how these galaxies were able to accumulate so much gas," he said. The findings suggest that each of these galaxies had at least one close neighboring galaxy. The interaction between these galaxies would cause gas to cool and trigger an intense episode of star formation, resulting in this extreme emission feature. Interestingly, the discovery also confirms the assumptions of astronomers who suspected these extreme galaxies are indicators of intense interactions in the early universe. As team member and Curtin University researcher Ravi Jaiswar said, "What's really exciting about this piece is that we see emission line similarities between the very first galaxies to galaxies that formed more recently and are easier to measure. This means we now have more ways to answer questions about the early universe, a period that is technically very hard to study," he said. In addition, this new conclusion is yet another example of how the James Webb Space Telescope was worth every penny of its $10 billion cost. Prior to this, astronomers simply hadn't been able to get a clear picture of star-forming galaxies that existed around 12 billion years ago. According to Gupta, the data quality from the James Webb Space Telescope is simply exceptional. It has the data and resolution needed to see the neighbors and environment around early galaxies from when the universe was only 2 billion years old. With this detail, we were able to see a marked difference in the number of neighbors between galaxies with the extreme emission features and those without, he said. The data used by the team was collected as a part of the JWST's Advanced Deep Extragalactic Survey, or JADE survey for short, the goal of which is to explore the earliest galaxies and open the door to future insights. As Gupta concluded, prior to James Webb, we could only really get a picture of really massive galaxies, most of which are in really dense clusters, making them harder to study. With the technology available then, we couldn't observe 95% of the galaxies we used in the study. The James Webb Space Telescope has revolutionized our work, he said. Of course, it should be noted that piercing the darkness to reveal the very first light is only the beginning. Billions of dollars and lifetimes of work have brought us to this historic moment as the science of James Webb begins. But all this is only the very first step on a journey of discovery that will take us from the first rays of cosmic dawn to the very ends of the universe. What mysteries and treasures await us along the way? And the untold depths of the sky? We're about to find out. What's interesting, however, even as James Webb is living up to the hype and its price tag by revolutionizing our understanding of the universe, Webb's predecessor, the Hubble telescope, is just showing that it's still in the game. The 33-year-old observatory, the Hubble Space Telescope, has just snapped a new view of a hazy spiral galaxy that once hosted a supernova explosion. The galaxy, formerly known as NGC 941, lies about 55 million light-years from Earth. Its spiral arms are bright but not very well defined, swirling outward from a bright core into a faint halo of dimmer glass. Hubble's Advanced Camera for Surveys, or ACS, observed the remnants of a stellar explosion within the galaxy. When some stars reach the end of their lives, they explode in a brilliant burst called a supernova, which can briefly outshine the entire galaxy in which it sits. This particular supernova, known as SN 2005 AD, has since faded, leaving behind seeds for future star formation. Hubble's view captures the galaxy face-on, showcasing the realm's spiral structure and hazy surroundings. Using the Hubble data, SN 2005 AD was also studied as part of a larger initiative to understand the environments in which hydrogen-rich supernovae, known as Type II, occur following the rapid collapse of a massive star, according to a statement from the European Space Agency, or ESA. However, the initial discovery of supernova SN 2005 AD was made by an amateur astronomer named Koichi Itagaki, who has discovered over 170 supernovae. As ESA officials said in a statement, this might raise the question of how an amateur astronomer could spot something like a supernova event before professional astronomers, who have access to telescopes such as Hubble. The answer is in part that the detection of supernovae is a mixture of skill, facilities, and luck. Supernovas can be detected by looking for brightness variations in the sky. These stellar explosions happen relatively fast, appearing very suddenly and then brightening and dimming over a period of days or weeks. The amount of data Hubble collects in only a few hours of observations might take weeks, months, or even years to process and analyze, which is why amateur astronomers play a key role in helping comb through the space telescope's images. Amateur astronomers are also able to spend much more time actually observing the skies than professional astronomers who are assigned to specific tasks. Many amateur astronomers have their own system of telescopes, computers, and software that allow them to monitor the skies and detect astronomical events that may otherwise be missed, such as supernova explosions. An online system called the Transient Name Server was established for reporting such discoveries. This is a big help to professional astronomers because with supernova events, time is truly of the essence, ESA officials said. After Itagaki reported the discovery of SN 2005 AB, professional astronomers were able to follow up with spectroscopic studies and confirm it is a Type II supernova. Then, Hubble was aimed in the direction of NGC 941 to get a better view of the supernova and its surrounding environment, which astronomers might not have otherwise included in their study. According to ESA officials, such a study wouldn't be possible without a rich library of previous supernovae, built with the keen eyes of amateur astronomers. As a piece of good news, scientists just announced that the solar system of the far future is safe from a run-in with a runaway dead star. Last year, researchers looked at the trajectory of a rogue white dwarf star called WD 0810-353 with the Gaia Space Telescope and predicted that it was due for an encounter with our solar system in around 29,000 years. While this may seem like a long time in human terms, it is a relatively short period cosmically speaking. For instance, the Sun won't run out of hydrogen and swell out as a red giant for another 5 billion years, destroying Earth and the inner planets in the process. While the Sun's fate is likely sealed, new research has revealed that our planet, at least, won't have to worry about being decimated by the chaos caused by runaway white dwarf WD 0810-353 after all. In fact, the rogue star won't just miss the solar system, it might not even be headed our way at all. As astronomer Stefano Bagnulo said in a statement, "We found that the approach speed measured by the Gaia project is incorrect, and the close encounter predicted between WD 0810-353 and the Sun is actually not going to happen. In fact, WD 0810-353 may not even be moving towards the Sun at all. That's one less cosmic hazard we have to worry about." But what exactly did Gaia get wrong? For those who don't know, Gaia is a space telescope that is currently building an extraordinarily precise three-dimensional map of more than 1 billion stars throughout the Milky Way galaxy. It does this by precisely measuring the positions of stars and tracking changes in these positions by returning this slice of the sky and observing it again to see what has changed. In 2022, astronomers Vadim Bobulev and Anisha Bajkova analyzed the vast Gaia dataset, searching for stars that appear to be heading towards our solar system. This led them to WD 0810-353, a white dwarf star, a type of dense stellar remnant left behind when stars with masses similar to the Sun die. Our own Sun will become a white dwarf about 1 billion years after its destructive red giant spell, when the swelled outer layers of the Sun will cool and move away. WD 0810-353 might offer a preview of what the Sun will look like at that time when it comes to within about a half a light year of the solar system, about 31,000 times the distance between Earth and the Sun. While this seems like anything but a close encounter, it is close enough that the gravitational influence of WD 0810-353 could disturb the Oort cloud, a body of comets and other icy bodies at the edge of the solar system. The Oort cloud is located between 2,000 and 100,000 times the distance between Earth and the Sun from the solar system's central star. When the cloud gets shuffled by passing stars like WD 0810-353, the star's gravity could send some of these loosely gravitationally bound icy bodies plummeting toward the inner solar system and Earth. So, what happened with the observations of this rogue white dwarf? What made astronomers think it was heading our way, and how do we know it probably isn't? Well, in fact, when making its observations of WD 0810-353, it turns out Gaia missed something important and unusual about this white dwarf. It has a strangely large magnetic field. As Eva Villiver, an astronomer at the Astrobiology Center in Spain and co-author of the study, explains, unusually, this old white dwarf also has a huge magnetic field. In astronomy, magnetic fields are crucial to understanding many physical aspects of a star, and not considering them can lead to misinterpretations of physical phenomena, she said. The astronomers had determined WD 0810-353 was heading towards us by calculating the white dwarf's radial velocity, the velocity of an object along the light of sight from the observer to that object. This is done by looking at the spectrum of light being emitted by the star and then splitting that down into constituent wavelengths that make up that light. If a star is moving away from us, that scrunches up wavelengths, which is the effect of shifting the light down to the red end of the electromagnetic spectrum, a phenomenon known as redshift. If a star is moving towards us, however, the wavelength of light it emits is stretched and moves towards the blue end, and is described as being blue shifted. The thing is that magnetic fields can also affect the spectrum of light from a star, dead or not, by splitting spectral lines and shifting lines to other wavelengths. To determine if this was the case with WD 0810-353, Bagnullo turned to the Very Large Telescope located in northern Chile, and in particular an instrument called the Focal Reducer and Low Dispersion Spectrograph 2, or FORCE-2 for short. FORCE-2 let the team get a highly accurate picture of the spectra of WD 0810-353 and see if its intense magnetic field was messing with Gaia. This is possible because light waves usually oscillate in all directions, but when introduced to a magnetic field, they start to oscillate in a preferred direction, becoming polarized. Using polarized light from this white dwarf, the team modeled the magnetic field of the dead star and found its trajectory and velocity could actually be the result of a strong magnetic field. That good news means the solar system is likely safe from this particular rogue white dwarf. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this, and to always improve. And as always, thanks for watching, and we'll see you next time.